In this lesson, we're going to go over how to use the explain command in Mongo. Now, the explain command in Mongo is very similar to the explain command in MySQL. And if you recall, in MySQL, we put explain in front of a select statement, and it showed us the path it would take in order to get that data, meaning whether to use indexes, which tables to get first, if it did a join, but it would go ahead and show you the execution plan. In Mongo, it's similar, but there are some differences. First, the statement actually does run, even though it doesn't return the data, so it can show you the actual execution time. But it also shows you a lot more data, a lot of the failed choices, and it kind of explains why it failed. So, in order to use explain in Mongo, you put it at the end of the statement, and you say db.user, or whatever the collection is, find whatever the key value pairs are, if there's none, and then explain, and in single quotes put the execution statistics. Notice these single quotes are slanted, so don't directly copy and paste this. But then it's going to go ahead and give us information like the type, which is a basic cursor, the milliseconds taken, if it was an index only. This is recently changed in Mongo, so we're going to go through a couple different examples. So right off the bat, I'm going to go ahead and say, let's do a find on user, where the last name is Smith, and explain the execution statistics. And if I give that a run, well, I made a huge mistake. I didn't start up Mongo yet. So we're at the OS prompt. What we should have done is type Mongo, and then type use ADB. Now if I do show collections, there is our user collection. Okay, so now if I write this, I'm going to make my window nice and large because it's quite a bit of info. I get a field here called Query Planner, and it's got some information. It says it's going to do where the last name is equal to Smith, because we said last name is Smith. That's the parse query. But then you see here it has winning plan and rejected plans. And there are no rejected plans, but over here it basically says it did a index scan on the last name index, and it says index name is last name underscore 1, because previously we created an index on the last name. And if I scroll down a bit, we'll see that it returned 1,000 documents in about 3 milliseconds, and it has a whole bunch of other information which is really not relevant to us at this point. But it does get very detailed. Where this comes in handy is if we have sharded or multiple servers running, and it will tell us all the different servers it ran on. Well, for now I want to do db.user.get indexes, just to see our list of indexes, and we can see we already have an index on the last name. Well, I'm going to go ahead and make a change here. I'm going to go ahead and drop that index. So how I drop an index is db.user.drop index, and I'm going to say let's drop the last name ascending index. And if I run that again, now we only have an index on the ID. In fact, let's change this to keys. Get index keys. Okay. So now what I'm going to do, I want to go ahead and we're going to start this over. I'm going to run this now that we know there is no last name index. And what we'll see here is more of a basic run, that it parsed the query, but it basically did a filter to say where the last name is Smith. There's a lot less info in the winning plan because it didn't use an index. And of course we'll notice here that it still returned with 1,000 records, but it took 33 milliseconds instead of 3 milliseconds, and it scanned 97,000 documents. Well, I'll tell you what, let's take another look. I'm going to create with another index back on last name, and I'm going to run that again just to see the difference. And what we'll see here is, look, there's a lot more here. All about the index that was used to search for it. But if I scroll down a little bit more, it had to go through the index, so it returned 1,000 records, but only had to read 1,000 records, or in this case, documents. And this was 1 millisecond. Again, 1 millisecond is a lot faster than 3 milliseconds if you're running thousands of queries per second. Okay, let's go ahead and create a little issue here. I'm going to go ahead and create a few more indexes. I'm going to create an index on first name, and I'm also going to create another index on last name descending. So I'm not going to create one on username. We're not going to do that right now. But if I go ahead and I show my indexes, I have, and this is interesting, one on ID, which is, of course, guaranteed, last name ascending, first name ascending, first name descending. I can technically have two indexes on the same data, one in an ascending format, one in a descending format. Okay, why did I create all these indexes? Well, if I do a query like this now, my question is which indexes will be used, because I'm doing a find where the first name is Ashley and the last name is Osborne. Well, we have an index on the last name. We also have two indexes on the first name. So let's see what it's going to do. Well, it's got a lot more data back. So let's see. It parsed the query. It did an and said where the first name is Ashley, last name is Osborne. Fantastic. Winning plan. It said it filtered on the last name is Osborne and used the first name descending index to go ahead and get the data. So I guess it went through and did the first name descending index, it chose that one, and then it returned the data and then filtered where on that after it got all of those. Which, in my opinion right now, I'm not sure that's the best one, because first name descending would mean the Z's are on top, but we search where the first name is Ashley. These plans are not always, how would you put it, foolproof. Sometimes these algorithms that choose which plan to take is not completely there or perfect. However, what we get this time is rejected plans. And over here, it said it was going ahead and use the last name index. It considered it, but for some reason it rejected it. It also considered using the first name ascending, but it rejected that one. And it also, let's see, it considered doing a full table scan. And then, this is interesting, it said it was going to do an index scan on the last name, and then an index scan on the first name descending. If you keep going down, it'll show you other plans of how it could have used those indexes in combination. It's just nice to see that it is considering these other alternative plans. And we got 22 records back in 5 milliseconds, but it did have to scan 823 records. If we keep going through again, there's a bunch of other information. These details are not too important. A lot of it, again, gets more important if we're running multi-server at some point. But it did go ahead and choose one of the indexes and go with it. Where we have an issue is what happens if we have multiple indexes like that and we don't know if we should delete it or not delete it. Well, they give us this thing called hinting. And for those of you who are Monty Python fans, no, I'm not talking about a hint is nudge, nudge, hint, wink, wink. What I mean by hinting is we can specifically say use an index or don't use an index. And here's what I mean. I'm going to run the same query, but I'm going to say, well, what if I drop all of the indexes and just run it normally? I could say hint, and I'll say $natural, :1. And that 1 there is just a placeholder. But what this is going to do is force it to just use the main full table scan instead of using an index. Now, this can be used to tell her one particular query to use an index or not use an index, or it can be used just to see if our index is doing anything. They're taking up space. They slow down inserts, updates, and deletes. Should we or should we not keep these indexes? Well, if we switched and dropped the indexes by putting in natural, it's going to run it naturally. And what did I forget here? Oh, forgot to put this inside of a squiggly bracket. And what we'll see here is, because I said hint natural, it did not use any of the indexes. You can see there are no rejected plans because I told it which plan to use. And instead of taking the 5 milliseconds, it took 42 milliseconds. Okay, well, that was a little slower, not horribly. But, well, what happens if instead of using that natural index, I want to specify an index? Meaning, I want to tell it, use the last name index. So let's try that. Now, the rejected plans again is empty, but now I've forced it to use the last name index. And we see, well, that took 2 milliseconds. Wait a minute. That took 2 milliseconds. By itself, it decided to use the first name descending index, which took 5 milliseconds. I'm making a better choice than the computer. And in some cases, this might be the case. Let's see if we can get it even a little better. What if instead of using last name ascending, I'm going to use first name ascending. And according to this, well, that took even 1 millisecond. So based on that, I may go back and say, let's look at the keys. And the fastest query was using this index. So maybe I'll go ahead and delete this one and this one. Why this is a really good invention is it used to be that if you wanted to test this, you would, in SQL, of course, delete the index, test it, and then go, oh wait, no, I need that index, and then have to rebuild it. And I've seen the rebuilding of an index on a table with more than 1 million rows run for 20 minutes, which means in those 20 minutes, everyone in your system, if it is production time, if people are accessing the database, are running without indexes, so their queries are going to be really slow. This lets you test indexes if they are needed or not needed without impacting your clients. So Explain is a really good tool, again, for getting the execution plan and figuring out which indexes are important or are not important.